Okay, so let's start. Thank you everyone for coming. This is going to be an advanced class on cryptography. Those who do not have background in cryptography, it's okay. It's not actually hardcore cryptography. This is actually a class on the evolution of proofs in computer science. So this class is really about proofs. That's what we're going to learn, and kind of how proofs evolved with the years, starting from kind of the 80s, mid-80s, all the way to today, and how we think about proofs differently today. So this is what this class is about. Actually, before I go into kind of the content of the class and what I'm going to be teaching, first of all, quick question. How many students here are not MIT students, but cross-registered students? Okay, a bunch. So do you guys have access? So I hope I made the website public. It's on Canvas. But now I think it should be public, so you should have access. If anyone has problems with accessing the website, just let me know. I'll try to fix it. So this class is meeting once a week, weekly, from 1 to 4 p.m. In terms of expectations or what, the expectations that you'll enjoy it. I hope you will. I think it's really, really beautiful material. But beyond having fun, I want to ask, I have two requirements from you guys. So one, I want to have scribe notes for the classes. I have written notes. I can give it to you to help you out. But so we have about, actually we have 11 classes total in this class. But we're going to have a bunch of, one day we're going to have a guest lecture by Oded Regev, he has a beautiful result. He's going to come here on October 6th and present it to us. So that won't need to be scribed. And then one day there's a crypto day, which also won't need to be scribed. Well, there's more. Anybody wants to sit? But for the rest, we'll need scribe notes. I'm happy if you want to do it in pairs to the scribe, unless we'll run out of people and then we'll need to keep it for one. So that's one requirement. And then I was told that I need to do something more. That's not enough. So we'll do a P-set sometime in the middle of the course. Okay? It won't be anything too difficult. It's mainly to make sure you're on board. But I really do recommend that before class, every time before, so here's a real homework, okay? Every time before you come to class, in the website, there's reading. I really recommend you look at the reading and try to read. So there's beautiful survey by Justin Taylor. There's a link on the website. The survey is on proof system. It's more of kind of the applied side of proof system. This is a more theory class, but he does have really beautifully written sections that are very theoretical that I'm going to link to. So I recommend, or you can think of it as informal homework before class to do the reading. I think it will be very helpful for understanding this class, and also after the lecture to look at the reading, and I think it will be very, very helpful. Okay, so any questions about bureaucracy stuff? Okay, so let me tell you a little bit more about what the class is actually about. So, proofs is something that has been studied in mathematics for thousands of years. And usually when people think about what a proof is, a proof, you write kind of line by line, and you can verify it kind of line by line to make sure the proof is correct. That's how, most people think of what a proof is. Okay, starting from the mid-80s, in computer science, in particular in cryptography, the way we thought about proofs started changing. This came about because of the idea of zero-knowledge proofs. So there was a hope to kind of construct proofs that reveal no information about why the claim is true. And in around 85, Goldwasser, Mikhaili, and Rakov kind of constructed the first zero-knowledge proof. By the way, this class is not about zero knowledge. Actually, it's not about crypto per se. It's just about kind of coming up with new proof systems. Do you have a question? But they wanted to construct these proofs that reveal no information. And to do that, they needed to change the model. Turns out they could not do it using kind of what we think of a classical proof. And the way they changed the model is by defining a new proof system, a new model, which is called interactive proofs. We're going to talk about this today. Okay, but they define this notion of interactive proof. So we're going to start this course by talking about what interactive proofs are, okay? And we're going to construct interactive proofs. In the 80s and 90s, when people thought about interactive proofs, usually the model is we think of the verifier as being efficient. For us, efficient means polynomial time, okay? But of course, you know, in practice, it has a more specific meaning. But for now, think of efficient as being polynomial time. And the verifier can be all-powerful. So the time complexity of the prover was not even a consideration. Actually, they called the prover Merlin, like he's a wizard, can do whatever the hell he wants, like infinite power. What we're going to talk about after introducing this model and giving some protocols, we're going to talk about the model of doubly efficient interactive proofs. And here what we say, no, the prover is not all-powerful. We don't have all-powerful machines in the world. Every machine is bounded. So what we want, yes, the verifier should be very efficient, but the prover should not be all-powerful either. So we care about the prover running time too. That's what's called doubly efficient interactive proofs. We're going to construct doubly efficient interactive proof. We're going to show the GKR protocol, specific protocol, and then we're going to show application of this protocol. And we're going to see application to really nice kind of models such as PCP, which is probabilistically checkable proofs, MIP, multi-prover interactive proofs. And in particular, we're going to show how to use this to get a kind of reprove a celebrated result, which is the IP equals P space theorem of Shamir. Okay? So this, if you don't know any of these buzzwords, I'll explain everything. I'm just kind of doing a very quick overview for those who kind of heard these buzzwords a little bit, and so you'll know what to expect. Okay, so up to here, no crypto at all. This is not at all about crypto, it's just about proof systems. Then we're going to show how to use cryptography to get our proofs more succinct, okay? And then we're going to kind of leave the idea, the classical idea of a proof that if the theorem is false, you can't cheat. It's impossible to cheat. Like there's no fake proof. There's no false proof. Okay, if the theorem is incorrect, there's no proof, period. We're going to use crypto to say, maybe they're false proof, but they're very hard to find. So the only way you can find a convincing proof to a false statement is by breaking kind of a hard cryptographic problem. You can factor large numbers, you can break lattice assumptions, and so on. Okay, so we're going to use cryptography to make our proofs more succinct. But then what's going on here is our proofs, we can make them succinct, but they're still interactive. And then we're going to show how to use this beautiful Fiat-Shamir paradigm, which is a paradigm for reducing interaction. And we're going to kind of study the security of this paradigm and show how to make this paradigm secure. Okay, so these are kind of results that have happened very recently. Actually, one of the students here, Alex Lombardi at MIT, was a Vinod student, was one of the people who came show kind of the security of this paradigm. So we're going to show it. We're going to use it then to show how to get our doubly efficient interactive proof, how to make it non-interactive anymore, so make it completely non-interactive. We're going to also show how to use this Fiat-Shamir paradigm to do kind of batch proofs non-interactively in very succinct ways. So taking a bunch of claims and kind of giving one short proof from them. And finally, we're going to show how to use that to go all the way to what's called a SNARG, which is a succinct, non-interactive argument. Argument is just another word for a computationally sound proof. So this is kind of very, very high level of what you should expect to learn in this class. If you didn't understand a word, what I said, then this is what the goal is, that you will understand this by the end of this class. Okay, questions before I start? Okay, I need a volunteer to scribe for today. Oh, fantastic, thanks. Okay, so with that, let's start. So let's start with the notion of interactive proofs. And before I go to interactive proofs, let me just, even before interactive proofs, let's look at the class NP, non-deterministic polynomial time. Even this class is about proof system, right? So what is this? This class is trying to, by the way, there's another chair here. For those who don't have a chair, there's one right here. Great. Great, so even before we go to the interactive setting, let's even think of the class NP. What is the class NP? If you think about it, it's all the languages that have a proof, that's the witness, that can be verified by polynomial time. Okay, so we want to think, here's the framework for this class is the following. We want to ask, we have, the verifiers are polynomial time, or even like, they're very efficient. What can you prove to these verifiers? Okay, so that's exactly what NP captures. NP is all the languages that you can prove membership in the language to a polynomial time verifier. Okay? So NP is exactly the set of languages membership can be proved in polytime. So can prove to a polytime, maybe I should say, can proved to a polynomial time verifier. So a polynomial time verifier can verify membership in the language. So far, so good? Okay, but NP is not that rich. Okay, so we want more than NP. Okay, so one thing we can add, so what is the class IP? The first thing so IP, interactive proofs, add two components. So in NP, the proof is classical. It's the class of languages for which a membership can be proved using a classical proof. Okay, like a proof that you can verify just like running a Turing machine. Okay? Interactive proofs are different in two ways. First of all, we allow interaction between the prover and the verifier. They can talk back and forth. Importantly, we allow randomization. Now note, what do I mean randomization? The verifier can be randomized, and there can be some chance that the theorem is false and he'll accept, but that's very, very small. Okay, we can make it kind of, if the communication complexity is, let's say, n, we can make, you'll accept a false statement probability something like 2 to the minus n. So we can make it very, very small. But there is a non-zero chance that you'll accept false statement. Okay, so in that sense, we weaken the model. Now, note, if there's no randomization, if we force the verifier to be deterministic, if the interaction, so again, the interactive proof is a kind of interactive protocol between prover and verifier. If the prover knew what the verifier is going to send, if he was completely deterministic, then the prover can just generate the entire transcript and give it as a proof. So it will really be NP. There's no point of this interaction. So really the power of this IP comes from the fact that the verifier is interactive. It comes from the fact that the verifier is interactive, is randomized, and the prover doesn't know what this randomness is going to be. So if I'm trying to prove to you a statement, I send you my first message, I don't know what question you're going to ask me. You're going to answer some random question, and I'll need to give an answer. And then I don't know what the next question. If I knew all your questions in advance, then there's no point. It's like, it loses the power. Okay, so really the power comes from the fact that there's interaction and the prover cannot predict ahead of time what questions he's going to get from the verifier. Okay, so any questions? Okay, so I didn't define this formally yet. I'll define it formally in a bit. But I hope I convinced you that, like, without randomness, this model is really useless. Okay, there's no point. How about without interaction? Let's say I had only randomness. Do I get more? And actually, so what if we allow only randomness? So proofs. So let's talk about non-interactive proofs. Where the verifier, V, is randomized. By the way, I forgot to say, please stop me at any point and ask me questions. I like questions. Questions are good for me to kind of slow me down. It gives you an opportunity to digest. So it's a great thing. So please, just at any point, stop me with questions. Questions? No. Okay. So good. So what about if we said if we get rid of randomness, we get nothing. What if we get rid of interaction and we just allow randomness? Do we get more? And actually, we do get more. Okay, and actually, this complexity test is a name. This is MA for Merlin Arthur. Arthur is known as a verifier. Merlin is known as a prover. So kind of the prover sends a message. Arthur, the verifier, can kind of toss coins and based on that decide if to accept or not. But anyway, the non-interactive randomized version is believed to be, I mean, it may be more powerful than NP. We actually don't know, but it seems there's some more power. And actually, let me give you an example. This is an example that will kind of be useful for us later, so it's not only an example. But let me give you an example where kind of randomness can be helpful for us. Okay? So suppose you want to verify, let's say you have two n by n matrices, A and B. These are n by n matrices. Let's say over 0, 1, or over a finite field. And let's say you want to verify, suppose you want to verify that some matrix C is equal to A times B. So you're also given, let's say, C. So you need to verify a task of matrix multiplication. Okay? We can do it efficiently. In general, the best known algorithm is something like order O of n to the 2, 3, 6, maybe, something like that. That's the best known matrix multiplication algorithm. Why are you looking at me? Oh, the number? Yeah, close. But turns out that if using randomization, you can do it more efficiently. Okay, so let's show how you can verify that a matrix C is a product of two matrices A and B in time order n squared. Okay, so kind of the best you can do because you need to read the input. Okay, so how will you do that? Here's the idea. So here's a randomized algorithm for verifying this. So let's assume that F, first assume, this is kind of without loss of generality, that F is much bigger than N. If not, you can take kind of an extension field of that, okay, embedded in a much bigger field. So just let's assume, if those who are not kind of comfortable with extension fields, let's assume it's just much bigger, okay? Then what do? Here's my algorithm. What I'm going to do, I'm going to choose a random element in the field. I'm going to consider X, which is just 1 r squared up to r to the n minus 1. Okay, so all the powers of r. I chose a random r in the field. I look at all the powers of r. And then what do? Yeah? Exactly. And then I'm going to check if C times X, I guess transpose, because I wrote it, is equal to A, B times X. That's my algorithm. Okay? So note, so note, this is just a vector, and vector times matrix, so to multiply a matrix by vector is time n squared as opposed to, the n to the 2, 3, 6. So this is more efficient. Why is it okay? Why? So of course it's complete. If these are equal, I'm going to accept. Okay? But if they're not equal, so why is it sound? So maybe you can convince me. Let's say they're not equal. Maybe you can still convince me that they're equal. That would be a problem. So yeah?
You could move the term over and write it as a polynomial that opens to r, and since the size of the field is much greater than n, it's less probable that like a random point
Fantastic, fantastic. So let me just repeat what you said a bit more formally. So suppose they're not equal. There's one row that they're not equal on, right? Let's focus on that row. So you can think of, when I do C times X, let's say C1, like the first row of C. When I do C times X, you can think of this as I look at this, the row, as a polynomial. So if you look at the first row, maybe I'll write it as C11 up to, or C10 up to C1 n minus 1. Okay, let's look at this n row. When I multiply by x, which is 1 r squared, this is nothing but sum C1i x to the I. Or, sorry, r to the I. So now what do I check? So now I know if this row, let's say it is different than the row here, then I have two different polynomials. Right? So if I write the row there, let's say as, I don't know, D1, D0, or D10 up to D1 n minus 1, let's say this is the row corresponding to A times B. If these are different, then I have two different polynomials that agree on a random, two random degree n minus 1 polynomials. So the polynomial is defined by this row. These are the coefficients of the polynomial. They're n coefficient. So it's a degree n minus 1 polynomial. So when would I accept a false claim? If there exist two things that are equal, that are different, there exists a row in C that's different than a row in A times B. So there exists a polynomial of degree n minus 1 here, and a different polynomial of degree n minus 1. And these two polynomials are equal on this R. But what is the probability that two distinct polynomials of degree n minus 1 are equal? It's just, this happens with probability at most n minus 1, the degree, divided by the field size. Right? Two polynomials agree, two distinct polynomials agree on at most, or the fraction, now they agree on at most n minus 1 points, and which is n minus 1 over f fraction of the field. So I'll reject with this probability. And if we're not happy with this f is not big enough for us, then we do everything over a bigger extension field. So we can accept. So our rejection probability will be high if the claim is false. Any questions about this? Okay, so far what we saw is that oh yeah. Oh yes, please. Thank you.
Is that Schwarz-Zippel lemma?
This is not Schwarz-Zippel lemma. Schwarz-Zippel lemma is similar, but in a multivariate setting. So this, good. So that's a good question. So thank you. So I just want to say, oh, by the way, I should tell you guys, this is being recorded. I hope it's okay with you. You're not being recorded. I'm supposed to be the one being recorded, but I think you should know that there's a cameraman behind you. But actually, I don't think I'm going to put this public. I mean, it's in the website for us. Well, now the website is public, so it will be public. I can make it private if you prefer. If people come to me and ask for it to be private, I'll make it private. Okay. Good. So the question was this Schwarz-Zippel lemma? And the answer is Schwarz-Zippel lemma is a multivariate version of this. Okay, this is for the single variate case. So the fact that two univariate polynomials of degree d, distinct, they're equal on a random value, they're equal on at most d element, d being the degree, is kind of from, I don't remember the theorem, like basic something of mathematics. You say Lagrange interpolation? Yeah, but Schwarz-Zippel is exactly that, but the multivariate setting.
So it's a generalization of that.
Exactly. The Schwarz-Zippel is exactly a generalization of this theorem, and it will come up actually later in this class. So yeah, we'll talk about that. Great. Any other questions? Yeah.
Are there any examples where like having randomness but not interaction can give you more than a polynomial time speed up or something?
Good. Very good question. So the question is, do we have examples where randomness gives you more speed up than just kind of a pathetic, this is not very interesting, right? So, or in other words, let me rephrase your question. Is the class MA different than NP? That's the question. We don't know.
So MA says that the verifier has to be polynomial.
Yeah, so so let me explain. There's these class called like MA, as many as you want. And the idea is M means Merlin speaks. Merlin is the prover, he's the wizard. A means Arthur, the king, he's the verifier, answers. M speaks, A answers. M speaks, A answers. So there's kind of these classes, MA. Here, MA means M, the Merlin speaks. Arthur kind of uses randomness and then kind of sends randomness. Well, he doesn't speak, Merlin doesn't speak again. But Merlin speaks, Arthur chooses coins, and then there's a verdict function that decides if to accept or reject. Okay? And we don't know if MA is different than NP. Yes?
So this actually is a like polynomial identity testing, right?
Right. Like you're saying this is like polynomial identity.
Yeah.
Yes.
So I give you a circuit, right? Supposedly bounded degree polynomial. I claim that it's identically zero circuit. You can check it clearly with this the multivariate Schwartz symbol.
Right. Right, but you're saying to test whether a circuit is
identically zero. Let's say.
But wait. You're giving us just as a circuit. As a circuit, testing if it's identically zero. But if it needs to be low degree, because otherwise.
Right. So somehow like it's syntactically low degree, right? Low depth or something, right? Low depth arithmetic circuit.
Low depth, like log depth arithmetic circuit. Then you're saying it has polynomial degree.
Clearly
it has polynomial degree. You can test it by taking a large field, extension field. You can test. You don't know how to predict if it's yes. Good.
We don't know how to de-randomize it.
How to
I
de-randomize?
think if we de-randomize it, then there are circuit load bounds, which means that you can de-randomize everything, probably, right? More or less.
There's you get some circuit lower bounds, but it's
Yeah.
Although that's a problem in promise BPP, not MA. Well,
It's
it's an MA, but.
No, why? Why is it not an MA? So you look at the class.
It is an MA, but it's a.
Also, right. Okay. Yeah. You're right. It's in BPP. Yeah.
So I just want to make the point that what Yael described is essentially the canonical problem in MA minus.
Okay.
Yeah.
Up to details, which I think they're going to defer.
Thanks. Okay. Thanks, Vinay. Yeah. Okay. So now let's go ahead and just define this class of NP. Of IP, interactive proofs. So, and then we'll show how kind of an actual, and we'll actually show why we believe this class is more powerful than NP. We'll give kind of a protocol that solves a problem that seems pretty hard. So let's see. So here's so what is an interactive proof? An interactive proof IP. This is a protocol between and possibly all powerful. Okay, I'm not a prover. P. Okay, so P can be run as long as he wants, and a polytime verifier V, such that here's the requirement one from the protocol. We want to say that interactive protocol, let's say between a prover P for a language L, for some language or some problem L. So the problem corresponding to his membership in L, that's a problem. Is X a member or not a member? So an interactive proof should satisfy the following. So it's a protocol such that it should have two properties, completeness and soundness. Completeness says that if X is in the language, the prover should convince you to accept. Okay, so if for every X in the language, if you denote, let's say, by T the transcript, so let's say P and V, which has secret randomness, the prover doesn't know what it is ahead of time, on input X, let's run this protocol, we get a transcript. Okay, so it's an interactive protocol. It actually, you can think of it, the protocol consists in two phases. First, there's interaction between they talk back and forth. Let's denote the transcript by T. Okay, often denoted like PV, that's kind of the protocol. The prover has R, both of them know the input X. They generate a transcript. And at the end, the probability that V, with his input, he gets the transcript, the randomness in X, the probability that he accepts outputs 1, when we say output 1, we usually mean he accepts, is large. Okay, let me call at least C. So, and C is going to be a completeness parameter. So, protocol between P and V for language L with completeness C and soundness S. Yes, I do mean all X and L. Oh, thank you. Thanks, Lali. Okay, so if it's in the language, he's accepted with high probability. There's some completeness parameter C. In most of what we see in class today, C is 1. Okay, you accept with probability 1. And soundness says this. Soundness says that for any X not in the language, for every X that's not in the language, no matter how you try to cheat, you'll fail. Okay, so for any cheating prover, or for any P star, because it can be any prover that tries to convince me to accept, the probability for the same T as above, the probability that the verifier, given the transcript, the randomness, and X, outputs 1, accepts, is at most S. Okay, so that's, if it's in the language, you should be accept with high probability, C is high. If it's not in the language, you should accept with small probability, S is small. Okay? Question about the model? Yeah?
Is there any restriction on S and C, or are they just
constant? Great question. What are S and C? Are they constant? So that was my next remark, which means that the question was right in place. So often, if you look at the literature, there won't be a mention of S and C, and C will be taken to be 2/3, and S will be taken to be 1/3. That's kind of a canonical. So when people say here's an interactive proof, often you think of S as 1/3 and C as 2/3, and this seems like very arbitrary, and you should be alarmed. So where do these constants come from?
I think it's possible to just repeat the procedure to
Exactly.
arbitrate it into 1 and near 0.
Exactly. So the reason why we don't care so much about these constants is because if you have an interactive proof with a gap between C and S, so for example, 1/3 and 2/3, what we're going to do is repeat the protocol. So let's say that it's 1/3 and 2/3. Let's repeat the protocol, let's say n times, and then we're going to accept if you're closer to C and reject if you're closer to S. Or so in other words, if more than C plus S over 2, like right in the middle. If more than C plus S over 2 are accepted, you're going to accept. If less, you're going to reject. In this case of 2/3 and 1/3, if let's say more than half repeated many, many, many times, you should accept. If it's in the language, you should expect to see about 2/3 acceptance. If it's not in the language, you should expect to see 1/3 of them being accepted. And if you repeat enough times by the laws of large numbers, you're going to kind of get closer and closer to the expectation. So you're going to be either very close to the 2/3 and if you're in the language, or very close to the 1/3 if you're outside the language. And there's very strong concentration. So if you repeat it, let's say n times, then now you're going to be accepted, or the soundness and completeness gap would be something like 2 to the minus n versus 1 minus 2 to the minus n. So you can really kind of very fast make these things go to 0 and 1, which is why often we don't really care about these. And you can think of them as very close to 0 and very close to 1. So if it's in the language, you accept the probability almost 1. If it's not in the language, you accept the probability almost 0. Okay? Great. Okay. Any question about kind of what an interactive proof is? Okay, I just want to mention one thing. This notation, like PV on input X, is overloaded. We use this notation to denote the transcript. We also use this notation to denote the verdict function, whether V accepts or not. And also, I'll use that in class, and also wherever you read, you'll see both of them kind of used. So it's good to get used to. So this sometimes denotes the entire transcript, sometimes it just denotes the acceptance or rejection bit of the verifier. And it'll be clear in the contents. Okay, so now the question you should ask is, okay, is this model more expressive than NP? What can we do with this model? What's the power of this model? So let me actually go to the punchline and say there's a celebrated result by Shamir from 92, I believe. And he showed exactly, oh, this model is very, very powerful. And actually, you can prove any p-space computation in this model. Namely, if I want to prove to you any language in p-space, take any language in p-space, I can prove membership in this language to a verifier that only runs in polynomial time. So that's Shamir. So p-space, we believe, is much, much kind of more expressive, stronger than NP. We actually don't know how to prove it, by the way, but we believe that's the case. So we believe this is a much stronger kind of proof system. Okay, and actually before, I'm going to show you actually now, I'm going to give you an example of the kind of the power of this proof system. But before I go into kind of the technicality, I want to step back for a second and kind of think a little bit about the story here, which is a very nice story. So, this introduction of interactive proofs, this model came about for the goal of doing zero knowledge. Nobody thought at that point about whether you can prove more languages, not more languages. The only thing you want is to hide. Okay, I just want to hide why a theorem is true. I want to hide the proof. I want to convince you, but hide. That was the only goal that kind of introduced this model. And it's kind of interesting how kind of very fast, like also, who cares about zero knowledge? This is a really interesting model. Let's see what we can do with it. And this kind of opened our eyes. Just the idea that we can shift from the traditional way of thinking about proofs to this interactive and randomized land kind of brought about a lot of really, really beautiful and fascinating results, including the fact, this is the first time to realize, wow, we can prove a lot to a polynomial time verifier, much more than what was believed to be what we believed we can do with a classical proof. So this was kind of really, I think, eye-opening and very interesting. So, okay, so now I'm gonna try to convince you of why this proof system, this model, is so powerful. by giving you an example of things, a problem that I can prove to you using an interactive proof that we really don't know how to prove using a classical proof. Okay, so let me give you the example. So here's the example. So the protocol is called sum check protocol. And this, I'm going to give you an interactive, this is an interactive proof for the following problem. So take any degree fix, or, okay, given a polynomial f, let's say from f to the n, so a multivariate polynomial of, let's say, degree d in each variable. Okay, I want a proof that sum of f b1, or let me just make sure how I wrote it down. Okay, sorry. So take any, fix any, subset h and f. You can think of h as 0, 1, you can think of a bigger set. I want you to convince me that sum f of h1 up to hm for all h1 up to hm in h is equal some value beta. Okay, so there's a fixed polynomial f. Let's say I know this polynomial. Either it actually has a succinct circuit, or maybe I have oracle access to it. So I'm a verifier. Let's say I have oracle access to this polynomial, or there's some succinct way to compute it. So I can compute this polynomial easily. Let's think for now I have oracle access to it. So I can kind of query it in some point in f to the n and get back an answer. I want to prove you're going to prove to me that the sum of this polynomial and h to the m points, and all the points, there's some set h, you can think of h as 0, 1, you can think of it bigger, and I want you to sum this polynomial on all the elements in the set h to the m. Okay, all of this is done over some finite field f. And there's a result beta. I want to prove that this sum is beta. Okay, I'm going to show you an interactive proof for this language. Okay. Now, before kind of you guys are like, seriously, why do I care about this language? Is it interesting? Where did I come up with this thing? Let me tell you, I think this is the most important protocol in all the literature on proof systems. Okay, we all use this protocol all the time. It turns out to be super, super influential. Okay, every single thing we'll use from now on relies on this protocol. Okay, so it turns out, and I'm going to convince you that later, but that this is a very, very important, actually, problem. Okay, if you have an interactive proof for this problem, it kind of gives you rise to interactive proof for many, many, many other problems. Okay, actually, we use this. If you give me an interactive proof for this problem, I can use it to get an interactive proof for all of p-space. In kind of a black box way. So really, this is the heart of coming up with interactive proofs. This is the most important interactive proof. Okay. So with that, let me show you the interactive proof for proving this. Okay. Any questions before we jump in? Yeah?
So just to clarify, so H is like a subset of F, like one-dimensional. So it's not like a...
Exactly. Exactly. You can think of H as 0, 1, for example. You can think of H as 0, 1, 2. Yeah. I mean, if 2 is in the field. Yeah. It's a one-dimensional thing, right? And you sum over, so as a set, you sum here over h to the m, sides of h to the m elements.
So H, like any of the two H's can be equal, or it doesn't have to be distinct.
It can be, you sum over all of them. You sum over also like 0, 0, 0, 0, 0, 1, yeah, all, okay. Yeah, h1 and h2 do not need to be distinct at all. Yeah, exactly. over all possible, yeah, you sum over h to the m elements, each one over all the possibilities. Good? Other questions? Thank you, yes?
So degree D in each variable just means like any variable is endless, like exponent.
Exactly, so yeah, good, great. So degree D in each variable means f is a polynomial, so you can write it as the sum of monomials. Each monomial, each variable has a degree. So I would say if you look at all the monomials, each variable has a degree at most D in each of the monomials. Okay, great questions, thank you. Any other questions? Okay, great, so let me give you the protocol. So let's do it. By the way, I want to tell you, I get such satisfactions from your questions. So if you just want to make me happy, which is a great goal on its own, you should ask questions. Okay. Ready for the protocol? Okay. Prover convinces a verifier that the sum f on h1 up to hn is equal to beta, where the h's are all elements in the set h, which is in the field. We have some fixed field that we're working over. Okay. How would he prove, what would he do? So here is the idea. The idea is the prover will first send this sum, this polynomial, but where the first variable is empty, is open. So he will compute, make it low. He will compute sum only over h2 up to hn, f of x, this is a variable, h2 up to hn. And he will send this over. Let's call this g1 of x. So he sends a univariate polynomial, okay, where he sums over h2 up to hn, but leaves the first variable open. Okay? What is the degree of this polynomial? D. Very good. So this is a degree D polynomial. The verifier checks that g1 is of degree at most D. If not, he rejects, because he knows that this is a degree D polynomial, multivariate polynomial. So he knows that each variable is a degree at most D. So if you send him something that's not degree D, he's like, you're cheating here. So he's going to immediately reject you. He will also check that sum g1 of h, I guess 1, let me call h1, that if you take g1 and you sum it over all possible h's in h, what does he expect to get? What would he check for?
Beta.
Exactly, beta, because the claim is beta. So he checks that this is a degree at most D, that when you sum over h's, you get what was claimed. Okay? If this does not hold, then he rejects. He immediately say, but I reject you. I'm not going to continue. If this holds, then he chooses a random T1 in the field. This is often a notation, left arrow, that we use for choosing a random. Okay, so he chooses at random a T1, a random element in the field. Not in H, but in the big field. Okay, you need to think of this field as being big. The bigger the field, the better the soundness will get. Okay, so he chooses a random T1 in the field. Good. Then what happens, the prover, in some sense, this reduces the problem from checking that this sum is beta to checking sum let me write it here, to checking that sum of f t is fixed, or t1 we call it, and then h2 up to hn is this fixed, I don't know, g1 of t1. We kind of reduced the problem to this problem, which is of one dimension less, because the sum is only over m minus 1 variables. Yes?
Let me see the verified polynomial plan here. What are we polynomial in?
Good. What are we going to put polynomial in? Very good question. When I said the verifier is polynomial time, polynomial in what? So he's gonna be polynomial. Okay, we think of f. I said f kind of has oracle access to it. So what polynomial in what? So what we're gonna analyze his runtime in a bit, but his runtime will depend polynomial on m, which is the number of variables, and on the degree. And we think of today, and actually like throughout the course, and it's common in this field, we think of f like that he can add and multiply things in order one time. Like it's a constant. And typically these fields are going to be, say, polylog, but we don't want to run, chase after these polylog terms, so we're not going to consider them really. Sometimes we do, sometimes we don't. It depends. But beyond so if you want to be kind of very pedantic, then you should log f.
Also h, maybe?
Yes, thank you. Yes, of course. Thanks, Surya. The size of h and log f. That's what's going to happen. But you're right that here the polynomial time doesn't really apply here, because I said that he has oracle access, so we're polynomial over. So this is what he's going to be after. But when we're going to use him for applications, you'll see it will correspond to polynomial time. But we're going to go over this when we analyze the protocol. Okay, so let's just continue. So let me actually start it. So let me even say, before I continue the protocol, let's continue the protocol with kind of a high-level idea of what we're trying to do here. The idea is the following. We want to catch a prover cheating. That's the goal of a proof, right? We want to catch you if you're cheating. So suppose a prover is cheating here. How will we catch him? The way we're going to catch him is when you tell him, you know what? Give me this G1. Okay? Now, he cannot give me the actual true G1, because the actual true G1 will not sum up to beta. Beta is the false thing. So if a prover cheats, if you try, I'm trying to let's come up with this protocol together, with kind of the goal of trying to catch the prover. So how do we catch a prover cheating? So the idea is we'll tell him, you know what? Give me this sum, but with this open. I'm going to check that this sum, like that the sum of G1 is equal to beta, and that it's low degree. If it passes, then this G1 cannot be the true G1. It can't actually be the real sum of f, because the real sum of f is not beta. He's cheating. So this must be a cheat. Now when we send him T1, and we consider so now we send him T1, and we kind of reduce the claim to claiming this. But with very high probability, G1 is also a cheat, because G1 T1 is a cheat. So G1 T1 is not really this sum, because they're different. G1 is different than the F. So we know that if they're different, they agree only on D elements. Okay, two distinct polynomials agree only on D elements. What's the probability that this T1 is one of the D? Very small. D over F. Okay, so think of S as really large. Great, so this is also false, actually. He gives me G1, but it's actually not the real F. He's going to claim it's the real F, but I know it's not. Now I'm going to tell him, next thing, I'm going to tell him, okay, give me G2. G2 is, G2 of X is sum. It should be sum F T1. I'm going to only sum over H3 up to HM. The X2, the 2 is going to be open, and then H3 up to HM. Okay, so we started by getting rid of the summing over H1. We gave him the univariate polynomial, or we chose a random T1. Now we're getting rid of summing over the second coordinate. We're asking for a univariate polynomial G2. What do we check? We check. So the verifier checks that G2 is of degree at most D. And what else does he check? Very good. So sum G2 and H, maybe I'll write H2, is equal to what? Exactly. G1 of T1. So essentially, we kind of, we check this polynomial exactly as we did before. Okay, so now, note, if in the honest case, of course, that's the case. G2, of course, is degree at most D, because F is degree at most D. And when you sum with over all of H2, you should get exactly G1 and T. That's how we, great. If this does not hold, he immediately aborts and say, I reject you. If he's happy, he's going to send T2 at random from the field. What am I going to reply with? What should the prover reply with? So let's see, G3 of X is what?
Sum over H4, Hn of T1, T2, and then X.
Very good. Very good. F of T1, T2, X, and H4 up to Hn. Yeah, again, we take, essentially what happened here, we reduced, after T2, we reduced the problem to proving a sum check over sum F1, T1, T2, H3 up to Hm, and we need to check whether this is equal to a G2 of H2, of T2, sorry. Okay, so again, each time we kind of get rid of one variable in the sum check. We start with an n-variate sum check, and each round we get rid of one variable. Okay, last one, what do we check here? We got G3, what do we check? What is
G3, H3 equals G2.
Exactly. So first, that G3 is low degree, is degree at most D, and some G3 is G2, T2. And we continue in this way until we continue until we got rid of everything. So in the last round, what will happen in the last round? In the last round, we will send Gm minus 1, Gm of like Gmx, which is f of T1 up to Tn minus 1 x. That's what he should check. That's what he should send. If you're honest, that's what you send. You peeled out off everything. Finally, you're left with Gm, which is f on T1 to Tn minus 1 x. And then the verifier is done. He'll choose a random Tm, and he will check whether this is indeed f of T1 up to Tm. We assumed he has Oracle access, so we can check if this value is T1 up to Tm. Okay, so finally, this is this, and verifier, I'm out of room, but maybe I'll write here. V chooses random Tm and checks that Gm of Tm is equal to the oracle he has, f on T1 up to Tm. That's the protocol. I'll give you a minute to appreciate the beauty while I erase the board.
Could you have a different set for each variable? And just,
You're asking, can I have a different set? I can have a different set, yes. Yeah, so the question was, do the h's have to be identical? And the answer is they don't have to be identical. You can take we didn't use that anywhere, and yeah. It's somehow we always use it when it is, but that's a very good point, because it's like, it seems more general, it seems like it can be useful, but somehow we don't use it. But that's a very good point. Yeah, you can, the h's does not have to be the same h. It can be sum over h1 up to hn.
Yeah, so in particular, h could be equal to f, right?
Okay, h could be equal to f. Yes, h could be equal to f.
How do you do the summation over the G1 of H1?
Sorry.
The first line, the summation over G1 of H1.
You will take time proportional to f.
Yeah.
But let's say that's okay.
I think your soundness decays also.
Say again?
Your soundness goes away.
Yeah, so we'll talk about soundness in a minute. Actually, if f is degree d, the soundness won't decay. Okay, let's talk about soundness, and then we'll see. Actually, the soundness won't, in general, usually when h is big, in applications, what happens often is when you take big H, the F turns out to be degree H, or H minus 1. So when we use this protocol, so, as I said, this problem, I'm saying, what do I care about this problem? Who cares about this problem? So it turns out we care a lot. It comes up all the time. The way we use it in practice, like the way it comes up, is the F that we use usually is of degree H minus 1 in each variable. We use it in a way that turns out to be the degree of F. And the soundness decays with a degree. So if the H is big, the soundness, if the degree is big, the soundness is big. But actually, if your promise that the degree is small, then we're good. We'll analyze it right now. Yeah?
Can you say something about what's so special about polynomials here? I see that they can only agree on d coordinates, and you can do the summation thing, but is there something more general happening?
Yes, great question. Love the question. So what's so fascinating about polynomials that comes up here? So why is this so interesting? Why is polynomials so important? That this comes up everywhere. So here's my take on this question. Everything can be, okay, first of all, polynomials are, in itself, they're very, very useful because of their power of error correction. So in other words, what happens, if you cheated once, we're going to amplify your cheat. That's kind of what we do here, right? You cheated once, we're going to, for a random point t, if you're low degree, then we're assuming that this prover gives kind of low degree all the time. If you give low degree, and you cheated, then the cheat must be kind of correspond to a cheat in a random point. Like at the end, a random point, t1 up to tm, you should be different. And that's kind of, we'll analyze this. This is just intuition, but that's kind of the beauty of polynomials. That if you're wrong almost everywhere. Because if it's not the correct polynomial, then it's different from the correct polynomial almost everywhere. That's the Schwarzschild lemma. And for the multivariate case, for the single-variate case, it's just the Lagrange interpolation, I guess it's called. But, okay. Now you're saying, okay, but that's just polynomial. Why am I saying it comes, what's so special about polynomials? Why are they so general? Okay, if you happen to have a polynomial, good for you. You won because it has such error-correcting guarantees. You're lucky. It's your lucky day. But what if it's why is every day a lucky day kind of thing? Why does this polynomial come up everywhere? And the answer is that you can actually embed many, many problems into polynomials. So there's a technique which we'll call low-degree extension. We'll see that pretty soon, if not today, then tomorrow, then next week, where you can kind of convert many problems into polynomials and then use the sum check. So that's often what we do. We take a problem, we embed it into a polynomial. We kind of extend it to look like a polynomial of low degree, and then we use some check to it. So that's how it will come up. Any more questions before we analyze the sum check protocol? Questions on the protocol itself, or yeah.
So sorry, just to follow up. Is there some version of SumCheck you can run on like some generic error correction codes, or do you need not only the error correction properties of polynomials, but also their like admin structure?
Oh, you're asking. You're saying this sum check. Do I really need this specific kind of polynomial code, or can I do it using arbitrary codes, kind of thing? Okay, so actually, this is a great question. There's a paper by Meir from several years ago, I don't remember exactly, where he shows how to do a sum check over more general codes, not any kind of code, but more general than that. Think like tensor codes, or Rachel, do you remember? You looked into it.
Yeah, it's tensor
Tensor
code.
codes.
So the multiplication problem.
Yeah, so he generalized it, not to any code, but he gave a generalization of the sum check protocol to work for a larger family of codes.
But when you trying to parse the question, what does it mean for the sum check protocol to work for
Okay,
more general?
good. So you can think of it as I'm proving something about, I don't remember exactly how his formalization was, but it's like I'm proving something about a code word, and I want kind of,
So sort of reinterpret this.
you can reinterpret this as, because you can think of this F as being an
Yes.
error correcting code. So does it work only for this kind of Reed-Muller? This is called the Reed-Muller code. Does it work only for Reed-Muller, or can you do it for arbitrary codes? And he proves it for arbitrary codes. So this is kind of, there's kind of, any polynomial is an error correcting code. It's a type of error correcting code. For a multivariate case, it's called Reed-Muller. For a univariate case, it's called Reed-Solomon. And so the sum check protocol you can think of it as a protocol for Reed-Muller codes, and then you can ask, is there an analog for other codes? And actually there are analogs out there. Yeah. Okay, any other questions? Yeah?
I think I heard someone bring up like making the size of H like the same as the size of
F.
if I hear it correctly.
Yeah.
In that case, wouldn't there be like not a point of doing this, because it's in poly of like the size of H and the log F?
Okay, you're right. So you're right. So if there is, okay, so let me go back. So the question is, what should this H be? What is this H? And the answer is this H can actually be all of F. Of course, if it's all of F, the verify runs in time, which is like the size of F, because he checks, sum over H. If it's all of F, he runs in time all of F. But maybe F is not that big. Maybe F is polynomial. Even if F is polynomial size, still checking this sum is much bigger than F, right? It's like H to the N, like F to the N, and can be big. So the hardness does not come only from F, it comes from N. It's exponential in N. It's the M that kind of makes it very hard. And so H can be as large as the entire field. And you can run some check over that too. It's still an interesting protocol. Yeah?
But if we use that, wouldn't we need to do this an extension of F or something? So that
Good. So, okay. Good. So the question is, wait, do we get any error correcting guarantees here? Because if we're doing over all of F. And I think the answer is yes. We don't need to extend it further. Because as we'll see now when we analyze it, the soundness error goes down with something like D over F. H does not come into play there. But we'll see that. Let's see that together. I agree. When you say that, you're like, yeah, that should, right? Things should degrade with age. But actually they don't. So we'll see that now when we analyze it. Okay. These are great questions, so thank you. Any other questions before we go to the analysis? Okay, so actually before we do soundness, let's just first do a sanity check on the kind of communication complexity and the runtime and so on. So first, let's see. This protocol has n rounds. Each round we kind of get rid of one sum in the sum check, right? So the communication complexity, our round complexity is m rounds, and back and forth, and 2m. I don't know if you want to count each one, or round is 1, 2. So let me just say order m. The communication complexity is what? So each time, one polynomial is sent, and one field element. So it's really, a polynomial is a degree d, right? So it's just d field elements each time, times m. So fine, we can do times, log f if you want to. So that's the communication complexity. Okay, what about the verifier runtime? So the verifier, he gets a polynomial, degree d polynomial, so d essentially field elements, or d plus 1 field elements, and he just sums them up. He checks that it's a degree d and sums them up. That's all he does. So it's really essentially the same. For m rounds, he has a degree d polynomial, and he sums them. I should put here maybe polylog then, because to sum, I'm assuming addition, multiplication take polylog f. Again, as I said often, I think maybe even in the notes, just in Taylor's notes, this is omitted. It's like the field, think of it as one operation. So just so you know, if you read things, often you won't see this part. Question?
Verifier also needs like each times different.
The verifier also needs to choose the t you send?
No, like you also need to sum over h.
Yeah, exactly. So sum over h is like h additions.
Yeah.
Okay. Yeah, he need. Sorry. Yeah. So okay, good. You're saying he needs to compute. It's still So right. So the verifier, he gets a polynomial. He needs to evaluate the polynomial in h. So yeah. So for m rounds, he gets a degree d polynomial. He needs to evaluate it. Oh, sorry. This does not have h. Yeah, he needs to evaluate it in h points, the degree d polynomial, and then a log f. Thanks. Good. Thanks a lot. Good catch. That's awesome. Okay. Great. So that's the verifier. As I said, the prover we care less about, but just, if you want to just, and by the way, this is assuming the verifier has access to f. He knows f. F is kind of, he has Oracle access to it. Because of course at the end he needs to check equality with f. So this we just assume he has Oracle access to f. And then the prover, what does he need to do? Well, he needs to do this computation. So he runs in time like h to the m. He needs to do all this sum. He needs to run, so the polynomial, so let's call it t sub f, is the time to run, to compute f. So he needs to compute f. He needs to do the sum over all f's, and he does that kind of m times, right? Something like this. And polylog h, polylog f, sorry. Yeah. So that's the prover's runtime. Okay. Yes?
Doesn't the fact that the verifier has has Oracle access to give you the purpose of using prover?
No. Good. Great question. No. So okay. So even if V has random Oracle access to F, he can compute this entire thing, but it will take him time h to the n, because he needs to compute a sum. So the goal, he needs to check. So let's say computing f once, it takes him one time. He can kind of ask. But to check the sum, he needs to ask this an h to the m question. Now think of h to the m is huge. even if h is 2, think of m as being big. M is like n variables, so it's like exponential. That's a great question.
But should I think of the description of f as polynomial, or?
Good. So you can, there's two options. You can think of the description of f as being polynomial. That's one option. Or that you can compute f in polynomial. It's like described by a polynomial size circuit. Or you can think it can be large, but the verifier has access to it. Somehow the verifier has like a trusted oracle that computes f for him. Okay? Great. Okay, so now yes.
What is T sub F?
Good. Yeah, this is just, sorry, this is just the time it takes to compute f. Thanks. Yeah, because he needs to compute, the prover supposedly doesn't have, he needs to actually do the computation. Okay, great. Yes?
Wherein that time complexity takes into account the prover finding G sub 1 of X. Like, don't they have to combine a bunch of terms in that order of D?
Oh yeah, but he runs in time f anyway. F is much bigger than D. So the degree is also always much smaller than f.
Okay.
So I'm kind of lumping it in. Yeah. Thanks. Great question. Yeah?
So if I want to really fast verifier, I can choose like a multiplicative subgroup or something for H, so I can evaluate polynomial faster. Can I do something else too?
Again, you're saying if you want to be even, you're saying let's say the verifier wants to be even more efficient than this, then what can you do?
Can I choose H to be a like special structure?
Okay, but you're changing the problem. What you're saying is, so the problem is H is given to us.
Yes.
And you want to prove. Now you're saying maybe if H has a special structure, maybe we can be even more efficient, is what you're saying. Good question. I haven't thought about it.
Like batch evaluation.
Yeah, like you can probably, yeah, probably you can. So what Vinod was saying, you can probably batch things, or probably, yeah. I think if you can choose H, if H is of a certain structure, then I think you can do better. But this is kind of the verifier doesn't choose it. Like that's what's given to him. Great. Okay, great. Okay. Any more questions? Yeah.
So why would an article compute f ever be useful? Like, isn't the size of f always going to be small because it's degree d?
Oh, okay. It's degree d, but it's m variables. So in general, degree d polynomial with m variables can have size like m to the d, so which can be very big. Great question. D to the m, sorry. Yeah. Great question. Okay. Okay. So let's go to completeness and soundness then. So what is the completeness of this protocol? If let's say the prover is honest, the statement is correct, with what probability will the verifier accept? 1, exactly. Because you'll just be honest, you always give the correct polynomial, it'll always be low degree, will always sum to what it should be, and you're always going to accept it. That's easy. The hard part is soundness. So let's do the soundness, and then after soundness, we'll take a break. Okay. So for soundness, here's the idea. Suppose, so let's look at it, suppose there's a cheating prover that generates a false claim. So suppose that the claim is false. Namely, this sum of f is actually not beta. Okay, so we start with a false claim. The first thing we know is that, and so fix any, so you fix a claim that's false. Fix any P star. He tries to cheat. Let's show that he fails. Like he won't succeed. Or succeeds with a very small probability if the field is large enough. So let's see. The first thing I want to point out, which I mentioned before, is G1 must be false. So it must be the case, no matter how he cheats, and he gives me a bad G1, okay? It cannot, if he's accepted, if the prover is accepted, then G1 cannot be sum of a, we call G1x, is not sum of f h2 up to hn. Because I'm going to check that it's equal to beta, but the sum of f is not beta. So the G that he gives me cannot be the correct f, like the correct G. Okay, so in other words, he starts the protocol by a cheat. I mean, the first message is not the correct polynomial. Okay, because the correct polynomial, if you sum it, you'll get the real beta, not the fake beta. Okay, that he claimed. Okay. However, at the end of the day, if you're accepted, the final check, when you check, then you check with respect to the honest f, right? And that verifies. So at the end of the day, when you left it with g to the, like the last one, gm to the tm, that's actually honest. So somewhere in the protocol, you had to move from a bad G to a good G. Okay, so again, here's the claim. So I want to argue I want to argue there must exist a round such that, around, let's say, I, so to cheat, there must exist around I such that GI is false, so GI is not sum of T1, Ti minus 1 x Hi plus 1 up to Hm. This is what it should be, but it's not. And yet, at some point, but GI plus 1 is actually equal to, oh, I forgot the F, is actually equal to sum F T1 up to Ti. So to cheat, you must go. So you start with an incorrect polynomial. We know that's for sure because assuming you're accepted. If you're accepted, G1 is false. Now, either now G2 is true, and then I'll show that happens with very small probability, or G2 is also false. If G2 is false, either G3 is true, I'm going to show that happens with very small probability, or G3 is false, until we're left with Gm. Which again, let's say it's still, I'm going to argue that if Gm minus 1 was false, Gm is also false, with very high probability. But if Gm is false, you're not going to be, if Gm is actually not F, then for random T, the probability that you'll get F is you'll be consistent with F is very, very small, because these are two different polynomials. And they agree only on D points. So what's the probability that you chose one of these Ds, one of these points, D over F? Okay, so let me be a little more formal now. Okay, so I want to argue that, first let me argue that, so first to cheat, there must exist some round where we go from false to true. Because the final check must be true. Otherwise, I'm going to check you with the true. So there must exist a round that you go from false to true. Let's see what's the probability of going from false to true. So, good. So what's the probability? So let's denote this event. Let's denote this event by Bi. Now let's see what's the probability that this event's happen. This is kind of a bad event, an event that you go from a incorrect, a false to true. That's for the verifier, it's a very bad event, because then he accepts a false statement. What is the probability that this bad event happened? So the probability of Bi, I want to argue, is at most D over F. Let's see why. So let's see, when is Gi plus 1 true? We're sending here, like the probability, let's fix, like we fixed already T1 up to Ti plus 1, that's fixed. Okay, so fix, and I don't care how, Ti1 up to Ti minus 1, this defines like what the prover gives Gi in the protocol, the cheating prover gives in the protocol. Okay, now the verifier chooses a random T. A random, so good. So this defines Gi, which is, okay, this defines Gi. Now the prover, the verifier, the probability over Ti that the verifier chooses this Ti tells you if Gi, this defines Gi plus 1. But when is, if, what do we know about when, if, we know that because the verifier is accepted, we know that some Gi plus 1 of H is equal to Gi, which is the wrong polynomial. So, sorry, and Ti. And this is the wrong polynomial. So what is the probability that for, so in other words, Gi plus 1 is the wrong polynomial. What is the probability that for a random T, it will be the right one? D over F. Because two polynomials that are different agree on at most D points. I choose a random point. The probability that it's one of these D's is D over F. So what is the probability that you cheat? And this is the probability that there exists some I such that BI holds, a bad event holds. Namely, there exists an I that you go from false to true on that I. By the union bound, this is at most M, number of rounds, times the probability of one of a specific BI bad event, which is D over F. So just note, H actually doesn't come up in the soundness. This is the soundness. Okay, so the soundness needs M times D to be significantly smaller than the field size. That's all that's important for soundness. Yeah?
So is the point that like you can pick at the H that you actually care about, and then you have some extension field F, and then like this really big field where you actually
Exactly, exactly. So the point is, if you're not happy, if F is not large enough, if it's not much bigger than M to the M times D, then you just make it bigger. You can take extension fields, you can take, so you just kind of artificially increase F, so that F will be much larger than M times D, and hence you'll get a small soundness error.
Parenthetical question here. So
Yeah.
in applications, looking ahead, what happens is you give an H, right, and the degree happens to be H, essentially, or H minus 1. And that's why it doesn't make sense for H and F to be the same. But you can
Exactly.
Some check you can disentangle these.
100%. So let me repeat it because I'm recorded, you're not. Yeah, because that's a very good point. The point is, for some check in general, it makes sense to consider any H. Even H, which is of size F, is interesting for the sum check protocol. Okay? In application, because as long as the D is small, of course. In applications, often it turns out that when we use the sum check, it turns out that the D is often equal to the size of H. Okay, because we kind of do this low degree extension which makes the field as large as H. And then if we take H, which becomes the degree, to be F, this is meaningless. So for application, often indeed H is small. But for the sum check protocol on its own, you can take H to be the entire field. Yes?
Is it true that any finite field can like it's easy to just put it inside another bigger finite field?
Yeah, okay, good. Yes, exactly. So let me, so there's kind of, you can take, so this is a fact for mathematics, you can take any finite field and embed it into a bigger finite field. And how big is the bigger finite field? Kind of as big as you want. So you can take any, loosely speaking, you can take any F and embed it into kind of a field F to the N. So when you can take N as big as you want. So you can kind of, that's what's called an extension field. So you can kind of extend it to as large size as you want, while still keeping F as a subfield. So operations in F kind of behave exactly as they did before, so without ruining this sum or anything like that. Yeah.
This analysis seems tight, right? Is it really the case that there is actually a cheating strategy that succeeds with?
Yes. This analysis is really tight. So I mean, if I'm malicious, I can always hope for the best. If it happens to be, I'm malicious, I gave you the wrong polynomial. Look, you may find, so I want to go from the wrong polynomial to the true polynomial. That's where, to cheat, right? That's what I want to do. Now, my wrong polynomial and the true polynomial, they agree actually on d points. Any two polynomials can agree on d points. So as long as the verifier, I'm lucky enough that this t is one of the d points, I'm in luck. I got a good polynomial, and I'll continue with a good polynomial till the end of it. Now I'm in kind of la la land, I'm happy. The problem is the chance, each round, the chance that you'll give me a t that's one of the d points is only d over f. And a union bound over everything, it's n times d over f. And if f is much, much bigger than n times d, then the chances that the prover will be in this la la land is very small. Okay, any questions, further questions about the subject protocol? Okay, so let's take maybe kind of a 5-minute break to stretch and so on, and then we'll show application. We'll start showing applications for this.